I haven't retired yet with a few $1 million. Eventually, I'll sell that startup and retire.
Oh yeah.
Hmm? You found it? Yeah. Great.
There you go.
Great. All right, guys, let's get started. So, we had the exam. We've completed like the first third of the class, right? Hopefully, everyone is caught up at this point. That was kind of like leveling everyone in a way, right? So, some of you have taken machine learning, and so that was not new to you. And then some of you hadn't taken machine learning, and that was new to you. But everyone can make a neural network, deep neural network now. Hopefully, classification and regression. So the rest of so now in the second third of the course, we're going to look at some advanced algorithms for deep learning. Um, and so, machine learning, right? And so we're going to look at transformers for the second third, however long that takes. And then after that, my goal is we're going to do the image processing things, right? GANs and stable diffusion. And then that's, basically how it is. So I think when looking at those algorithms are way more complex than say what we've been doing before. But actually, by doing something that difficult, it's just going to really help you to understand how neural networks really work. Do you know what I mean? So just by looking at the complexity of them. All right, so looking at transformers and everything, which is the first topic that we're going to cut. It's going to take a few weeks. Um, so looking at transformers, will take time, right? So this is not a thing that we can cover in one class. We'll go over them for a while, but they're very interesting, and so we'll go over that. Okay, so you guys, I'm sure have heard of transformers, right? So you know Chat GPT and Claude and Gemma from Google and all those tools. So they're based on this algorithm called a transformer. And so really that's where the AI is. So everything that we're going to do is from scratch in this course. So the goal here is really to understand how the algorithm works as opposed to using it heavily to solve other problems. So the other course, ITS 530, focuses on that. So 530 is more of a transfer learning class, right? So if you want to use a pre-trained transformer, fine-tune it to solve your problem and get good results, then that's the course for that. The goal of this class is really to understand PyTorch as well as possible. So, we're just going to try to go over some of the basics of how it works, okay? So it's got a lot of interesting ideas, but at the end of the day, I think it'll take away the mystery of AI. That's my goal, right? At least my goal in this course is that by the end of it, that whole mystery of, how is this AI going to kill humanity and all that, it should go away, right? It's just some code and some things like that. So you'll definitely also face some of the challenges of this. One of the things that's going to happen going forward is that things are going to get bigger. Even if I wish this thing would just like somehow go away. Yeah, sorry. Uh, some of the challenges of dealing with large models will also come into play here, which is basically we need to use GPUs even if we just use very little data, right? So everything from CNNs and so on, which are the next topics right now, it's CNNs, transformers, attention, and diffusion models. So these are the concepts that we'll be covering basically for the rest of the semester. I would say it's really just two algorithms, honestly, and they're just complex basically in how they work. Okay, so as I was saying, we're going to need to use GPUs. I was able to get GPU Scholar, the Purdue Scholar website or Cloud AI. So you should all have access to it now. Okay. So I will provide some details for you guys at some point, and you'll need to basically do your homework assignments using this tool going forward, most likely. You can't all log in during class, for instance, because it's like a queuing system, so it's limited to the number of GPUs that we can have. So if all this whole class try to get in and get GPUs, it wouldn't work. Okay. So but yeah, just keep that in mind. All right, that you do have access. For those of you that already know how to use a Scholar, go ahead, try to log in, see if you can get in there. And like I said, if not, I will provide some links later on. Okay. So that's not a priority right now, but it's something that we're going to be doing. All right. The other thing I wanted to address was the homework assignment. So I posted a homework assignment. And so I want to stress that. So if I'm going to go to section 1, give you a chance to ask questions. So the homework assignment should be this one, DLN homework. It's really, you have 2 weeks to complete it, so it's not due today. I know that the way that I do this in the system is I kind of say it's due today, but if you notice, I leave it available until October 9th. So it'll just mark it as, I kind of do it at a range kind of a thing. So just make sure you have even though it might mark it as late, you're not going to lose any points, okay? So submit your homework. You have until October 9th to submit it. Does that make sense for everyone, guys? All right, so that's maybe I didn't tell you this, but this is kind of how I always do homework. All right, so anyway, what matters really is until it's available. After that, if it closes, then you can't submit it. Got it? Does that make sense? All right, so I'll talk a little bit about the homework just to kind of illustrate. I believe I provided, yeah. So basically, as I said, I believe you guys know how to create a simple neural network using PyTorch. That's the goal of it. You have to use PyTorch to build the model, okay? Now, can you use sklearn for performance metrics? Sure. I mean, I gave you the function, right? What I said is you can't, please don't use like a decision tree or something with sklearn or a neural network. That, that defeats the purpose of what you're doing, right? So the whole point is to understand how to do these tensor operations and to kind of practice with that. Got it? Everyone with me on that one? So you need to implement your models with PyTorch, train them with PyTorch, but otherwise performance metrics, pandas, if you process data like that, something that's perfectly fine. Got it? All right. The other question is, how do you submit? You can submit your files, but please prepare a report like a PDF or a Word document, just that has, the key things, right? So what was the data set? What were the sizes of things, the training process, and then performance, like what was precision, recall, F measure, the confusion matrix. Most of these data sets are just classifications. So I ended up just giving you 3 classification data sets. Got it? Now, these are some materials I've had before, so they were even built already in TensorFlow 1. You can read through all the information there if you'd like, but obviously I didn't provide the PyTorch code, so you should be able to convert it to PyTorch. And hopefully that'll give you some help. Read, all the details. You need to identify what the inputs and outputs are of everything. Does that make sense? Are there any questions on the homework?
I don't think so.
Nope. All right, perfect. All right, so great. So yeah, just you have 1 week and submit it by next Tuesday. By the way, I think next or Monday, sorry, is fall break, if I'm not mistaken, right? Isn't it fall break? So no class, but still submitted by then. Okay. All right, so that's everything out of the way. We talked about, I'm still grading your exam, so some of you may have a grade, others don't have a grade yet. I'm going through that right now, and I'll be posting. So as you saw, the exam is pretty simple and easy. All right, so so we've talked about the topic. So now today, I'm going to talk about transformers, right? So we're going to start our discussion of transformers. It's probably the hot topic, so I figured I'd make it interesting for you instead of, the boring CNNs or something. All right, so those are also very interesting, and we will discuss them together. And if you think about it, you can create like, stable diffusion, for instance. You can go in and give it some text and it generates images, right? So it's a combination of all the tools, really. All right, so but yeah, so the goal for the next few classes will be to look at GPTs to really dig deep into how they work. And I honestly believe that if you understand that, then you can build any neural network because they're going to be even easier than what we're building. Okay, so we'll be talking about that. All right. So let me go. So just like I did before, I have some reading material here. You can take a look at chapter 10, Transformers, GPTs, and BERT. And basically, these are my notes on some of the terminology and everything that goes on. So I'll kind of go over that, a lot of the terminology. I'll give you a little bit of the history, actually, of how this came about. Yeah, and then these are also sometimes called the large language models, all of that nice information. So this is basically what I'm going to do in class for the next few classes. We'll start to dissect a lot of this code, but you can definitely please read through it, and it might help you a little bit. And then we'll look at the attention mechanism, just like the simplest one. And if you notice also in your linear algebra problems that you had from the beginning, attention was already discussed there as a separate entity. Okay, so take a look at that. And then as you can see, the goal of these models is to generate text. Don't expect them to be like ChatGPT, right? So it's not going to be coherent or intelligent like ChatGPT, as that takes a lot of resources. Right, but the goal here is to look at the text. Even if we were using pre-trained models and we use something like a GPT-2 that's pre-trained, it still wouldn't be like the greatest thing, but it would be better, of course. All right, so anyway, so that's read through all the text. We will talk about BERTs a little bit as well and how they work. Yeah, and here's some, yeah, so this is a bit long, but definitely read through it. Okay, so that's kind of your reading assignment. All right, so let me go back to the graph. Give you a little bit of the history. All right, so I like to use this graph. It's kind of the graph that I think about when I think of transformers. Okay, that's as small as I can get it. All right, so the transformer was created basically by Google in 2017, right? Created at Google. The rumor is that they didn't even know what they had. It's kind of one of those things that, I've heard some people speak about them. They were obviously, the paper was about language translation. They were in fact translating from English to French and German, those languages. So they, what did we have before, right? So we're going to think about some of the issues in the history. So before we had RNN, something called recurrent neural networks. I don't like recurrent neural networks. I've never liked RNNs. I don't like coding RNNs. I don't like dealing with RNNs. And this has been something that I've never liked. There's some people that like it. There's another mechanism called the attention mechanism. That's really the fundamental piece of this whole thing, probably. Right? So they're still not even clear exactly how they work. But I mean, the attention mechanism is clear, but how transformers learn and et cetera. But one of the key pieces is probably the attention mechanism. So what happened was back in 2015, 2016, they had RNNs, and they even put this mechanism called attention in them. So the RNNs had attention in them. Okay, so people thought, okay, these are great. Then in 2017, they created this transformer for language translation, which had an attention mechanism. And basically the selling point is something like, we made it so it scales in parallel. So that's kind of the idea, right? I've heard that people even like at FAIR and Facebook and everything looked at it and okay, so it's got attention, It deals with sequences. And what's the contribution? That it's parallel, and that they even then back then it didn't have great reception, is what I'm saying, right? So the performance apparently of the translation was incremental, but not significant, like people would expect when there's a huge development that the performance jumps by like 15%. These were incremental performance increases in the translation task. You have a question?
No.
Yeah. And so basically, I'm just giving you guys like the story of the transformer because it's really interesting. So the point is, people were doing RNNs, people loved RNNs, they were really into RNNs, and they had an attention mechanism. Now comes this thing, it's similar, and the only thing is that it's made in such a way that it runs really well in parallel. Okay? So what do I mean by that? So everything that, transformers, RNNs deal with a problem called sequential data mining, sequential machine learning. So basically the idea that you have a value and then you predict the next value, and then with that value, you predict the next value and so on, right? So these are like time, it could be time series or sequential ML, sequential machine learning. So that's what RNNs were for. So language, of course, is really good. It's basically that type of a problem, right? What is language? I say the cat is going to sleep. There's a sequence. And I look at the previous information to predict the next token and so on. So that's what RNNs did. But the problem with RNNs was that they needed to be sequential. So it's like they needed the previous information to do the next one, right? And so that's kind of taxing on like the CPU basically. So it became an issue that you can only do so much. And so they weren't very efficient at running like that. Do you guys see that? So then we've obviously had GPUs for a long time. Since about 2007, they've been using, they started to use GPUs to parallelize machine learning and training, okay? So basically what happened was the transformer is an algorithm that was literally created for the GPU. Do you see what I'm saying? If you want to think about it, they took the sequential problem, right? But they made it in such a way that it ran really efficiently on the GPU in parallel. And these are the kind of things that we're going to look at, as we start going through the algorithm. Do you guys see that? So basically, that was the big development, actually. And so it wasn't clear that they were going to be very good, but eventually they came out in 2017. And I believe like within a couple of years, Google and whoever it was really started to use them very efficiently. And it started this whole revolution that we're having today. Okay, so they recognized what was there and they just started using it in various ways. So initially, it was used for translation, right? But over time, it's been used. Obviously, I'm sure all of you have used something like ChatGPT. So it's not just used for translation anymore, right? All right, so that's kind of the history of it. But yeah, it all started with that famous paper from 2017. It's by Vaswani. It's called "Attention is All You Need." All right, and like I said, some people will say this whole thing that RNNs had this vanishing gradient problem, and then even though residuals had addressed vanishing gradient, the vanishing gradient problem, the transformer did a better job, basically, of that. But honestly, the consensus right now is that the two things that are really important for the transformer are the attention mechanism and the fact that it was built literally for GPUs. So it's almost like transformers exist because of GPUs. Okay, that's kind of the idea. All right, any questions, guys? All right, so the architecture of a transformer is this whole big thing right here. Okay, so it's a pretty big thing. So just to give you an idea, this little square called an encoder layer is basically like one MLP that we were doing. Do you see what I'm saying? So like in the previous third of the class, we've done regression, we've done MLPs, and we've done like, deeper neural networks, right? So think of just that part of the neural network in just one encoder layer. So what that means is there's a lot, it's very deep, right? Do you see that? Imagine that this is an MLP, and the output of that becomes the input to the next MLP. And the output of that becomes the input to the next MLP, and so on. So these are very deep, very complex networks. And in fact, they don't just have, I'm calling them MLPs, they're actually called feed-forward networks. They don't just have feed-forward networks, but they're also going to have several other mechanisms in there. Okay, including something called the attention mechanism that we will look at. But the attention mechanism is, just think of it as a neural net. Okay, so the name is actually, it gives you a lot of information of the main idea of this. They're called transformers. So think of it as you have a vector. The vector goes to some architecture of the neural network to produce another vector. And that vector becomes the input to the next part, which is then takes in that vector, does some neural network processing to produce another vector. Do you see what I'm saying, guys? So that's the basic idea with transformers. Anyway, so in this example, for instance, the example of the original transformer, the translation, you were going from English to, let's say, I think this is, did I put the, let's say Portuguese, yeah, PT, Portuguese, right? So let's say that it's translating from English to Portuguese. So to keep it simple right now, just think of it as English sentences go in through here, right? And then what goes in here is what has been said already of the Portuguese sentence. And then it'll produce the new Portuguese word, right? So basically that's the generative model. It translates from an English sentence to a Portuguese sentence, but it's generating that Portuguese sentence almost one word at a time. So the cat. So then the output of this becomes the input of this, and it just does that auto-regressively, as mentioned. So don't worry, we will obviously do this in code. I'm just kind of giving you a high overview right now of how it works, okay? Are there any questions so far? Yeah, go ahead, please.
Like we are using different layer of encoders here.
Yes.
What's the accuracy gonna be for that one model? Like if the accuracy is less for one model, how can we improve the accuracy of particular models?
Improve the accuracy of the model?
Yeah. Like,
what do you mean?
If we are using the outputs of one model to the other one, right?
Oh, okay.
Yeah.
So you're talking about the output from this to become an input? Yeah. Okay.
If there is like less accuracy.
You think if this is really bad, then it's just deteriorating over time, right? That's kind of what you're saying. Yeah, I get that. Think of it as the brain, and it's like it's gonna receive some information, process it a little bit, and then use that information to process a little bit more, and then use that information to process a little more over time. So we don't necessarily look at the output here, but you're gonna look at the output over here. So think of it like this. I have English and Portuguese sentences, right? So I give it English here, and I get it goes through, think about it. It goes here, 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 all the way through here. Then it comes in here to all of these layers, and then it comes out here. So all the weights in this have to be learned, okay, during training. So what happens initially, let's say that you've done only one run. So you give it English, it's going to give you really bad Portuguese. Do you see that? That's all that you look at. But as you continue to train it, what might happen eventually is that you give it English, and this Portuguese is starting to look better and better and better. Yeah, go ahead, please.
Good, bad. Like how can we identify the particular the model is bad from tracing back? Like how can we test?
How can you figure out if this layer is bad? Oh, so what you might be assuming is that each one of these architectures is different. They are, in fact, the exact same architecture every time. So that's actually a good question. So for instance, think about it as, for now, keep it simple. A vector of 784 goes in, a vector of 784 comes out. And then for the next layer, a vector of 784 goes in, a vector of 784 comes out. and the architecture is the same. Some schemes share the weights, other schemes, like the one we're going to do in class, they all have their own weights.
Oh.
Does that make sense?
Yeah.
Yeah, so that's a good question. Like I said, this is a big machine, and we need to break it down into parts to start to understand it, okay? So, but yeah, so when you see here encoder layer, and there's 6 of them, just think of it quite simply as you instantiate a class called block, and then just iterate 6 times and create a list of 6 instantiations of that class, and then you can use all 6 in sequence. Make sense? Yeah, that's a good question. So, right, so this is the transformer original by 2017. The other idea that I'm going to convey to you is actually the architecture that was designed in 2017 is pretty much the architecture that is being used today. The only thing that changes is that maybe instead of 6 encoder layers, it could be 100. You know, they scale up that number of layers, but the ideas inside have not changed amazingly, either because people just don't understand or because there's no need. Right now, the only need has been to do 2 things: give it more data, give it more computing power, and it just does better. So in general, it hasn't been an architecture thing, which is one of the amazing things about transformers. It's like a general learning machine. It's really strange. Okay, it's almost like humankind, like humans, stumbled upon this algorithm. You know, it's almost like a discovery of this thing, and although it was engineered, and it's very general for a lot of things. Got it? It does need a lot of data though. But anyway, so that's the goal. So right now I'm just going over this graph, kind of laying out some of the terminology. All right. So one thing I will say is, so ChatGPT, for instance, let's kind of mention that. So ChatGPT is actually not a full transformer. It is only one part of the transformer, like half of it. So transformers actually are made up of a section called the encoder and a section called the decoder. And within that section of the encoder, you're going to have things like encoder layers, and you're going to have feed-forward neural networks, attention layers, and embedding layers. That's generally speaking all they have, right? And these are ideas you already understand about how neural networks work. It's just that you have to put them together. So I'll just mention the parts right now. We're going to dig deep into a lot of these as we proceed in time. I will also not do the translation problem because that's like taking the most complex problem. Instead, we're just going to take the GPT problem, which, believe it or not, is actually easier. So in this example, though, you start with some English sentence. You obviously cannot give text to neural networks, right? So what you do is you give numbers. So we need to find a scheme to go from text to numbers, right? And this is going to generally be called embeddings. So we need to talk about what embeddings are, right? So we're going to talk about embeddings. There's also going to be the problem of sequence, right? And you're going to look at it and probably be amazed by the clever way that sequence is encoded. So what I mean by that is, you know, in language, which is where I'm going to be, what I'm going to be basing my examples on. In language, it's important to know the order of things, right? The cat went to the store, right? Or the store went to the cat. I mean, this could be a mobile store, right? So that, you know, if you didn't have that order, right? If you don't encode it in some way, then the meaning is lost, right? And so that's one of the problems that needs to be addressed. And that is called positional encoding. So it's another technique that is used, right? So basically, initially, we give it English sentences, we convert it into the embeddings. So you can see apply embeddings and positional encoding. And what we get is, and this is critical when thinking about transformers, is I would say that you should think in terms of tensors, right? So tensors are key, and that's why I've stressed a lot about you doing those 109 problems, because you want to think in terms of dimensions, right? So we always think it's the best way, I think, to understand how transformers work. So if you look here, I've encoded dimensions in this. So basically, let's take a look at this example here. So I'm going to give it English sentences, right? And notice I'm saying a vector of n by 40. So what that means is, rows and columns, right? So the row n is pretty simple to understand, a batch of 6 sentences or 6 tweets or 6 paragraphs, whatever. And they can be random. It doesn't really even matter, right? But it's just a full sentence and then another full sentence and then another full sentence. Do you guys see that? The other thing is with something like an RNN, the sequences were variable length, right? But in a transformer, because we're using GPUs and things like that, we need to actually have like these buffers of a fixed size, right? That's really critical. Like almost like when in CNNs, as we will see later on, the images are always, 226 by 226 or something like that. It's a similar idea with transformers. So in this case, and my numbers are based on the original paper. They started with sentences of size 40, let's say. Do you guys see that? Does that make sense? So basically what we're saying is I'm going to feed initially a tensor of n by 40. Let's say 16 sentences, and each sentence has, for now, let's just keep it simple. It's not exactly like this, but let's just say 40 words. Got it? Okay, so then you might ask the question, but what? Not all sentences have 40 words in them, okay? So if the sentence, so you have to pick a value that's big enough, right? Remember that you're going to be constrained by your GPU and RAM requirements. This is this is the world that we live in, and we're constrained by the hardware that we have, right? And so if you want to achieve high scale of learning for these models, you have to give it tons of data. It has to run fast and efficiently. So right now, obviously, n by 40 was in 2017. We have better computing power now. So this size has gone up for sure. But so if the sentence, so once you pick the number like 40, which is big enough, then most of the sentences are going to be less than 40. If they are less than 40, then basically you just pad it. So that means at the end, you put like zeros, and then you'll have a way, something called masking, which will come into play later on, is critical, will be used to kind of pad that these are not tokens that we care about. Does that make sense? If a sentence goes over 40, you truncate it and you lose that information. It doesn't matter. Okay? So that's basically the idea. So this is really important that when we read through the code and we try to understand how GPTs, how transformers work, that we always think in tensors. So now to your question of, something goes in, something goes out, this vector that goes in as n by 40 will become n by 40 by 512. So it goes from a 2D to a 3D, right? So instead of a square to a cube, if you will. What is n? It's still the batch size. What is 40 is the sequence. But what changes now is that for every one of these 40, right? Every one of these 40 words, before you can think of n by n comma 40 as 40 IDs. Do you see what I'm saying? So, let's say that the is 13 and then cat is 3. Then this would have in there, in the first sentence, 17, 3, 5, the IDs of the words, if you will. So instead of giving it the word the, we're going to give it an ID of a number that if we go to a lookup dictionary or vocabulary somewhere, we can find that word or that syllable or something called that subword. Make sense? Yeah. But once we have IDs here, like, 17 and 3, that's not enough for the neural network to learn. That won't be enough, unfortunately. So what we have to do is we create something called an embedding. That's where the embedding, the magic comes in, okay? And what the embedding will do is it'll take that 3, right? And it'll map it now to a vector of whatever size you define here. So 512. So think of it as I had 17 in there and 3 and 23. Now, instead of that 17, I plug in a vector of size 512. And in the next one, which was a 3, I plug in a vector of 512. And in the next one, a vector of 512. So that is basically that embedding is actually what the neural network will recognize a word by. So it'll use that information to say, oh, this is so-and-so. Does that make sense, guys? So that's a really important concept. The positional encoding is actually very similar. So the positional encoding is going to be basically, you have two of these tensors, right? It's going to be n comma 4512 plus n comma 4512. So one is the embedding of the, the actual word, and the other one is going to be the embedding of the position. Okay? Because also 40 is the order. So now instead of having 17, 3, 23, what do you have? 1, 2, 3, 4, 5, all the way to 40. You know that 3 goes before 25. And then for that, you're also going to learn an embedding. That's one approach. And that embedding is a positional embedding in this case, because it's taking into account the position that is there. And there's other approaches. There's one called the sine and cosine approach, but either one works equally well. And, I don't know which one they're using nowadays, but both have been proven to work well. Does that make sense? So the best way, in my opinion, to understand transformers is to think of them as tensors. Think of and the key name, transformation. So what is happening now that I started at n by 40 and created n by 40 by 512, you might have other questions. So for instance, these embeddings, where are they coming from? Well, these embeddings are actually learned by the transformer. It's, if you've ever heard of embeddings, you would know that in the past, through techniques like word2vec or something like that, you would have a sentence, run it through some algorithm, and then you'd have a vector that you can download off the web about that word the or car, and then you could, those were embeddings for words. But that's not how transformers work. So transformers actually have the embedding mechanism built in. And so what does that tell you? It tells you that initially this vector of n by 40 by 512 has only random values in it. Okay? But as you start the training, all the training of the neural network, etc., those embeddings, start to become good values. And what are these embeddings? They're just weights. Just like everything that we've done, y equal wx plus b, they're just embeddings. So we'll look at this idea of embeddings a little bit more. Talking about this means that we need to talk a little bit about encoders, right? So we'll talk about encoders as a neural network function a little bit later and other things. They're simple concepts, right? So like word2vec, encoders, transformers, they all use this idea of encoding, and that's a similar concept. But as we dig deeper, right? So right now we're at a very high level, just to give you kind of an intuition. Any questions so far? Nope. All right, so n by 40 by 512, right? So again, the name transformer, what does that mean? It just transforms. It takes an n by 40 by 512, it goes into some neural network construct, n by 40 by 512 comes out. Then what do? Take that n by 40 by 512 to the next layer, goes into some construct, n by 40 by 512 comes out. That's it. That's the simple concept. All right, so you can see that. So for now, I'm not going to explain what an encoder layer does. But what I can tell you is it takes in as input n40 by 512. Out here, n40 by 512, which goes into the next layer, n40 by 512. And keep in mind, it's going through neural networks that initially have random weights. Over the training, they start to become really good. So in our examples for the course, we'll use the Scholar GPU that we have available here at the university. Each of you can have one GPU, and you can train a few books from. I'll show I'll do my example with one book, but you guys can use several books from from Gutenberg, etc. And just that's kind of the idea, right? So we're going to go in depth on the algorithm and how it works. So n by 40 by 512 goes in, n by 40 by 512 comes out, n by 40 by 512 goes in, and so on, right? So it goes in through all these layers, until in the end, notice what comes out. So this is called the encoder, this orangey part with 1, 2, 3, 4, 5, 6 encoder layers. And that's because that was the original Vaswani paper, right? So it had 6 encoder layers. So this is just replicating that architecture. And what comes out of it is the n by 40 by 512. Do you see that? Now, that's the end of the encoder part of the transformer. So then there's also a decoder part, which works a little bit different. So if you look just, if this is the encoder part, then basically an encoder is just a big embedding machine. That's literally what it is. If you think about it, it took your n, it's still there, the 16 or so, the batch of 16. The sequence is 40 is still there, but this 512, the values in there have been seriously modified. Do you guys get that? So it's like it's learned, hopefully. So it's learned how to create really good representations of the tokens there. So some people just use encoders with that. So basically they take out the whole decoder part, it's gone, and just use the encoder part. So basically they take in something like this and they get N40 by 512, and then they think, okay, how can I use this? You see that? And that's where something called BERT, if you've ever heard of BERT, came about. So I think BERT was created by Facebook, I want to say, or Meta now. Yeah, so maybe. And at the end of, once we finish GPTs, I'll discuss BERT. It's here in these notes. So the architecture is there. So basically what you do with a BERT is you take the encoder part and then do additional things to it, additional logic. But basically it's just using the encoder assets. Questions? Now, in the original transformer, what they did is they wanted to take the English sentence, right, encode it into something that remember that what comes out of here is something that the neural network learned. You don't really know how it did it or even what is there. But what's important is because you're training, it's good because it's gonna be, those outputs are optimized to achieve a good score at the very end of the day, right? So if it's trying to translate to Portuguese, right, then it translates and it's bad, and then it starts to get better in the learning process. So then the model is assigning weights and it's paying attention to things that it thinks are important, right? Because it has these constructs built in that let it do that. Okay, but you don't quite know what it learned exactly. That's not exactly clear, right? Because that's how neural networks work at this level. Does that make sense? Any questions? Any thoughts? Yeah, please. Sir.
I mean, it learns to predict the next words. Like how exactly it learns, I think that's what you mean, right?
Yeah, what I mean is, well, the architecture is there, right? So the architecture is there, but insights as to what it's finding important, I mean, and especially, I don't mean in like a simple problem, but how does it know how to reason? How does ChatGPT know how to reason a little bit, right?
A lot of experts say it's pseudo-reasoning, it's not actually.
I get that. I get that. I'm not one of those people that says that AI is here, but at the same time, you have to admit something's going on. So there are patterns that it's learning. Either it has, for instance, what you might one way that I would describe it is possible that there is a grammar of intelligence, just like there is a grammar of language. You know what I mean? Like there's a grammar of language, English, Spanish, whatever there's a grammar of language. But there could be grammars of other things, a set of rules of how things were, how do we have chains of thought and actually can look at these chains of thought and arrive at certain, like thought in conclusions at the end. And so it could be as simple as, even though we as humans don't know it, there is a grammar of how we reason out. And if that exists, it'll find it, because that's what neural networks do. It find patterns. So when I say that we don't quite know what it's doing, that's what I mean. It's like, did it discover some weird grammar of logic that we just don't know exists, but it's starting to pick up on, and so that's what I mean by we don't know. The fact that we do know exactly how the architecture works, right? And we do know that. And we don't know also the embeddings, are really important, and what is being captured by those embeddings. But yeah.
Yeah, but the
Yeah.
loss it's training on, it's basically predicting maximizing the probability of the next word, right? That's specifically
It's learning,
typically.
it's adjusting the weights, right? It's taking the input data, learning the embeddings, learning the weights of the neural network to predict something that when it's compared to the real, it achieves a good score. That's basically
But typically, like in the real wise training, it's basically predicting the next word from the current word, right?
it's predicting, so we'll see here, for instance, in how the GPT is trained, we'll see this. So you have, let's say a sentence here, and you're going to have the same sentence over here, but just shifted by one. So it learns, given this input, what are the next ones in the training. And then in the testing, you're going to start with, let's say, 3 words. And given those 3 words, it's going to predict the 4th one. And then now it's got 4 words. So the 4th word, if you notice this arrow, sends it back as input here. And now given those 4, it's going to predict the 5th one. But it is looking at the whole thing. Yeah. All right, so that is the GPT part, okay? So that's the GPT part of it, which is actually what we're gonna focus on, okay? So here, this is the output of the encoder, as I said, is n by 40 by 512, okay? Now, that's called the encoder part. This part over here, as you can see, is the decoder part, as it was made for the transformers for language translation, okay? So in this case, we would give it, also notice, n by 40. In this case, it would be the predicted words. So this is where it gets a little bit confusing sometimes, right? So everyone will say, as Omer said, right? You give it 3 words, and then it gives the 4th one, and then I use those 4 words to predict the 5th one. During training, that's a really bad idea. Do you see that? Really bad. Why? Because if I'm training and I give it 3 words and it predicts a 4th one, and then I use that one, and then it predicts a 5th one, what's going on in there? There's some error going on. So like one time it should have predicted egg and it predicted dog. And that comes in, and that error is in there. So what happens in these autoregressive models in the decoder part is that you have one of the concepts called teacher forcing. So in teacher forcing, what you do is you take imagine you have the sentence over here, the cat is sleeping. That input is the same as the output over here. The exact same sentence, just shifted by 1. Do you guys see that? So whereas I had the cat is sleeping as input, as output, I would have cat is sleeping today. You see that? Just shifted by 1. Okay? So it's the same sentence, but this one has the next one, always. So think of it as shifted by 1. We'll do examples of this to hit that idea. Okay, it's really important. But yeah, so when we're training, we're gonna give it with teacher forcing. We're gonna use the real data. We're not gonna use like predicted data during training, because then that would make for a really bad model. All right, so, and you'll see how that trick is done. Once it's trained, though, then the beauty of the model is you can give it 5 things or 3 things, and boom, it's going to start predicting until 40 probably, which is the size of the block that you're using. Okay, so that's kind of the nice thing about it, and that's the generative model, and that's how, in essence, how ChatGPT works. Okay, so we'll see that. So again, so basically for the translation problem, whatever came out of the encoder was being used in the decoder section. But also the Portuguese sentence was coming in as input, and the shifted version of it was the output, right? So what happens next? Same thing, n by 40. So this is good to think about the transformer like this. N by 40 means batch of n, which are separate sentences. 40 is the length of the sentence, right? 40 words, for instance. Then notice over here, same thing happens. Apply embeddings and positional encoding. Do you guys see that? So what we do, notice that the tensor goes from n by 40 to n by 40 by 512. Why? Because in that 40, we had ID 17, 3, 5. Now that ID 17, 3, 5 becomes embeddings of size 512. Okay. All right. So this n by 40 by 512 then goes into the same thing as before. The decoder layers just transform a tensor of n by 40 by 512 into another tensor of n by 40 by 512. And then the output of this becomes the input of that, and so on all the way to the end. And guess what you get here at this point? A tensor of n by 40 by 512. That's what you get. All right, so that's the basic idea. And then finally here, you do have a new mapping where the n by 40 by 512 needs to be mapped to n by 40 by vocabulary size. So in that case, let's say your vocabulary is 70,000. That's where you actually get the word. Got it? So it's going to be a transformation of the neural network. It'll take in n by 40 by 512. Out comes n by 40 by 70,000. But one of them will be the word that you're going to choose. Okay? And so that's basically how it works, how the transformer works. If you were using this for something else, like predicting audio or time series data, you could just stay at n by 40 by 512 and map that to n by 40 by 30. And maybe that's the number of features you have, because remember, what you're going to do at that point, whatever comes out there, you compare to the real. Do you see that? So you will always have these vectors of your real data. And then you decide what the model outputs, compare the two, and that's it. Just like we did with classification, in a sense, is the same idea. All right. All right. So that's the transformer idea, right? If you notice, the decoder layer, very similar to the encoder layer, except that it needs to account for the fact that it's going to get this encoded output as an input to some of these layers. And so there's going to be something in there that handles that in one of the steps. And so when we dig deeper into this, we'll see that. Anyway, to me, the translation thing is not that exciting, right? So what's exciting is really the GPT, right? So that's where we're going to focus on. And then once we finish the GPT, you guys should be able to understand the BERT pretty easily. You know, you may be able to code it as a homework assignment on your own. It should be pretty straightforward, right? But we'll spend most of our time just dissecting the decoder. So anyway, so looking at this graph, the transformer is this whole thing. The encoder is this part, which leads to creating something called BERT. And then this part over here, the decoder part, is referred to as GPTs. It's called technically the decoder, but that's what GPTs are based on. Like literally, they're just a decoder, half of the transformer. Okay, so that's basically so now this is what we're gonna look. So we're gonna totally ignore these arrows, and instead, and actually, we're gonna ignore the problem of language translation, and instead, we're just gonna do English to English. So really then what happens is what you're going to give it is the cat is going to sleep, you know, something like that, right? So that's basically what we're going to try to do in the next example. All right. And so we're going to dig deeper into the architecture. All right. So, some of the things that you need for transformers, obviously, you know, we're going to be playing with tensors a lot. So if you haven't done so already, go through those problems I gave you. So there's a lot of problems related to this in that set. The attention mechanism, we will explore that one. It can be complicated, but actually there's a simple way of looking at it. All right, so we'll talk about attention. Keep in mind, there's a lot of versions of attention. There's a flash attention nowadays, etc. We're just going to look at the original attention, and then from there you guys can add, but it's the similar recipe. Embeddings, I've talked about embeddings already. Mask, it's certainly one of the concepts that's a little bit confusing. We'll talk about that one. Keep in mind, there's a lot of masks for transformers, right? We only need to we will only focus on, let's say, the decoder part of the mask, so GPT type of masks. Positional encoding, we'll do a couple of examples of how this works. This is actually a simple concept. And this allows this is really important because you need the information about sequence, but you also need to be able to parallelize the training. With RNNs, you were not able to do this because you have to calculate in sequence all the previous values to calculate the next one. This is something that transformers do for you, right? But with the trick of positional encoding, which is this, which is like a very simple. Tokens, we'll talk about tokens for sure. Tokens just means the number of words. There's quite a bit that goes into that. I'll start with the simplest example of just letters in the alphabet. Really, tokens or the vocabulary is based on like syllables, but it's really called subwords. So instead of syllables are a construct of like human languages, but these syllables are not necessarily like normal syllables. They're just combinations of words that have certain frequencies. So the most frequent or least frequent. So there's algorithms that are used for calculating those, something called BPE encoding, etc. If time permits, we'll go over that, at least some idea of it, but just think of it as a separate algorithm. So it's like 2 passes, go through your data, do something like BPE, generate the vocabulary. It's a mapping of integers to these subwords, right? And then you use that basically for the training. As I said, in this simple example, I will just use letters, like the 26 letters in the alphabet and some special characters. So this is an example of what your input looks like. So for instance here, your sentences will look like this initially. So this would be 4 by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 4 by 10. That's the original tensor that I'm giving the model. 4 sentences. They're not in the same, you know, they're just randomly selected out of the book. And if you notice, these are the IDs representing a word or a letter or a syllable. Okay, and then at the end, they can be padded if they don't fit, if they're smaller than the size of the buffer. Make sense? Any questions? All right, so please read through this. Hopefully this will be useful to you. So the GPT, which stands for the Generative Pre-trained Transformer, was, I think it was Google, again, I want to say, I can't remember, but probably Google is who said, let's take just a decoder of the transformer and see what happens. And that changed history, right? So there's definitely a lot of amazing models right now. So all they did is they took this architecture, right? Notice where I have my arrow here, so the decoder part, okay? So the GPT uses the decoder only part of the transformer. And then, as I said, the input of the decoder varies depending on whether you are training or predicting. If you're training, the input to the decoder is the sentence itself. When training, a mask is needed here to prevent the model from seeing all the words it is trying to predict. And this is called a look-ahead mask. So we're going to use these masks to kind of predict what's coming next. If you are testing, the input is just the previous words before the word you are trying to predict. So keep that in mind because it can be confusing, but hopefully it makes sense that you should not be training, guys. You should not be training when you're predicting, right? So in that case, we use this technique called teacher forcing, which is right here. So I provided the definition of teacher forcing, read through it, but in essence, make sure the data is accurate during training by just taking the same sentence, shift it. That's it. All right, and then we're going to do the implementation of a GPT from scratch, which is basically what we're going to do during the rest of the class today. We're going to start this process, and I think this is really helpful. This and something like Stable Diffusion, because it really covers everything. Like and it like forces you to use different ideas. This code needs to be very modular, and it's got to be very object oriented. And if this is why when we were doing the first third of the class, everything was object oriented, because maybe there it seemed like overkill, but here it's essential for things to actually be reasonably understandable. Okay, so we'll use that approach. But yeah, so this is the code as described, and so on. So now one last thing here that I've had this idea several times today, and I keep forgetting. We know the code for the GPT. It's right here. Like I'm literally gonna give you the code to create a GPT. So why is it that all of you can't just like take that code and start your own startup and become super wealthy? Yeah, Henry.
Probably because we don't have enough GPUs to train.
Exactly. You don't
Or
have.
reading data.
Yeah, exactly. Because you need massive amounts of data and you need massive computing resources. That's like the limiting factor. All right. So it takes millions of dollars. I think I heard GPT-3 took like $8 million or something to train, right? And I don't know the specs. You have to read the paper, but it took a long time. Upwards of 1,000 GPUs running in parallel. That's not straightforward to do. There's actually very few people in the world that are very good at that because there's a lot of issues like the thing breaks, and it's a very difficult thing to get that a data center with thousands of GPUs all running the same job. Okay, it's not a trivial thing. All right. So anyway, but with one GPU is what you guys will basically work on. Okay, and you'll see. I mean, because at some point students do this. You just want to use your laptop because that's what you're used to. But then after a couple of days of nothing happening, you'll switch over real quick to a GPU. Okay. So like I said, these are provided by the university, so I'll make those available as soon as I can post the links online. All right, so hopefully that, we answered the question. So we have the architecture, but you don't have the massive amounts of data. Actually, the data is available also. I'm pretty sure there's been a few releases by probably Meta and some other people of a lot of data. So you can actually go and get a lot of the data and train these models. But the problem is you have to do it with GPUs, multiple GPUs in parallel, build these clusters, and that's not a trivial thing. I mean, you need software like Kubernetes or things like that just to build these clusters and maintain them efficiently. Okay. Any questions? Yeah, please, sir. Yeah, go ahead.
Every time we ask GPT,
Yeah.
does it need to use all the GPU and the power of the GPU to process it?
That's a really good question, actually. So the compute cost of training versus inference. So IBM or whatever said, okay, we can't compete with NVIDIA on training GPUs, but we will compete on inference CPUs. So that should answer the question, right? That you don't need the same amount of power. So you basically need it for training. For inference, you can use a CPU, for instance.
Like in that case, can we be able to get the trained models from any source, like probably Meta releases it?
The pre-trained models?
Yeah, pre-trained models.
Yeah, so that's what I was saying. So this course, I don't cover fine-tuning. That's what 530 is for. So in 530, we'll use Hugging Face, for instance. So it's easier in that sense that you can download like a GPT-2 or whatever and do something called reinforcement learning through human feedbacks, or maybe just regular supervised learning, SFT, and fine-tune the models. So you can download with Hugging Face a GPT-2, fine-tune it for horror stories, and then now when you ask it a question, it's gonna give you a spooky answer, for instance. You know what I mean? So yeah, but that's what the 530 class is. And this class is more about like understanding the algorithm itself. Any other questions, guys? All right. Okay, so what we're gonna do now in the next half of the class today is we're gonna start going through the code. All right, so I have this available, same place in the GitHub. So it should be GitHub And it should be in here. Deep learning algorithms. Yeah, go to second edition here. And it should be this one, chapter 10, transformers. So it goes with the material I gave you for reading. If you can see here, I have BERTs, GPTs, and things like that. So let's go, should be here, I think. Yeah. So this one, there's several things going on here. There's the linear algebra, attention, and NN. So we'll go over this a little bit later. But these are the just intuition on how the attention mechanism works. But really, this Jupyter notebook that you see here is what we're going to be focusing on. Okay. So just like I did in previous examples, we're going to go over all the code of the GPT. Keep in mind, we'll go slowly. Okay. So it's difficult for me to like just tell you everything about every single part of it. Right. So it's quite involved. And, and my goal is that we understand every single part of it. This example takes Huck Finn. So this is the Adventures of Huckleberry Finn. It's from the Gutenberg library. And so basically the idea is we're going to train that model on that book. Okay, so we're just going to start to look at some of the issues necessary to train the model. And this is the Jupyter notebook. So we're going to download this and kind of go over all the details. As you can see, at the end, we should be able to do something like ask it questions and get an answer. Okay, and it's actually, it's actually pretty built in, which is funny to me. Like, I think the first time that I learned about this concept of ChatGPT and you ask it a question and it gives you an answer, and it's like the GPT itself is made in such a way because you give it something and it just starts generating, right? So give it a question and it'll start generating something hopefully related to that question. And there's tricks you can follow so that the answer you're getting gets better and better over time. Okay. But that's kind of, so we will explore all these ideas. So we will explore the idea of generating basically, and all the things that we can. All right. All right. So anyway, so this is the code. The neural network itself is quite complex. So this is the actual simple version of it. But what you're not seeing is that this little piece here requires all these different classes like the multi-head attention, the block, the feed forward section. This should be the head, which is the attention head and the actual attention mechanism and so on. Right. So it's basically very modular and object oriented. Okay. My goal is not for you guys to memorize these things, but just to kind of get a really good understanding of how they work inside, basically. Okay. All right. So it's 6:16. This is a good stopping point. So let's take a 10-minute break. We'll come back at 6:26 and we'll just download this, the code and basically start going through it. Okay. So yeah, so it's 6:16. Let's take a 10-minute break.